training in spacecraft development, and the usual education and outreach in the STEM subjects. And the final thing was to demonstrate that you can kick off and produce a satellite in less than 12 months. I'm not sure we're going to do that. We might get the satellite produced in less than 12 months, but then there's the hanging around waiting for the launch business, which everyone's so familiar with. The other thing is it needed to support at least 3 primary payloads, as well as the platform. UKube 1's got 5 payloads, but actually it's got even more than that, because one of the payloads has several payloads inside it, and the FUNcube transceiver is another payload. This is the time scale. It's not to scale, so to speak. What happened to the laser pointer? We don't have a laser pointer. Right, okay. Ah, it's in the box. No, someone's stolen it. Well, never mind. I can go and point. I can just go and point at things. It's easy enough. So we've got the launch and early mission phase, which is the first few orbits. Then we've got a nominal mission stage, and then we've got end of life. And after 25 years or so, we hope that the satellite will deorbit, and that's required by the Outer Space Act, that the satellite is designed to deorbit in less than 25 years. The interesting bit from the point of view of AMSAT, apart from FUNcube, is that end-of-life operations may well see the satellite handed over to AMSAT-UK, should they wish to use it. Launch and early operations. Thank you very much. Right. Launch and early operations is the first thing. Of course, it gets deployed. It's being deployed by a pod. The microswitches turn everything on. The command and data handling system initiates pretty much straight away. And as soon as we can, we try and work out where we are and try and capture a few images using one of the cameras on one of the payloads. After about 5 minutes, deploy some antennas, activate the beacon, deploy the solar arrays, and start to try and stabilize the spacecraft. We're hoping to get the spin rate down to less than 20 minutes in about a day, and establish ground contact at that point. Then we'll have a phase of checking initial health checks and everything else, work out where it is, get the position sorted out, and start the stabilization procedure, and then it'll be in a standby mode probably for a while, and then we're going to start nominal mission operations once we're sure everything is working. So that's going to be a while. Of course, the other thing is we might well put the satellite away in the pod, and then it could be up to 120 days before it's launched, when we won't have any way of communicating with it. It'll be off. Mission operations. Primary payloads are going to be operating in sunlight only, just a matter of power really. They'll be working on a scheduled basis, so we can turn things on and off at certain points in the orbit to do certain things, like say take photographs, that sort of thing. FUNcube will be in sunlight. It will be doing the educational type work and the outreach, and in the eclipse and outside of the sort of classroom hours, it will start doing the transponder mode. And we're controlling it via packet transmissions from some ground stations, which I'm going to talk about a little bit later on. We've got an S-band downlink, which is a very high-capacity downlink. It doesn't need to work for the mission, but if it does, it'll be great, because it means we can download lots of really interesting pictures. So end of life, this is the bit that might be of more interest to people here, which is after about 2 or 4 years, so it's not very long. This is supposed to be launched in 2012, so maybe 2014, something like that. It'll start to be pretty much used as an amateur satellite, and hopefully the payloads will still be operating as well. And how long it lasts, well, who knows? It might last no time at all. It might last for the full 25 years. We're hopeful it'll last for a lot more than 2 to 4 years. The plan is to have it in a low Earth orbit, minimum of about 600 kilometers. We're hoping for a little bit more than that. The usual sort of 95-minute period, something like that, sun-synchronous, circular. And in that orbit, it should deorbit in less than 25 years. Not entirely sure about whether it will do that. So recently there's been this thing added, which was the spoiler, which we all spoke about yesterday. So that adds a little bit of atmospheric drag, and as you can see it's got solar cells on it, so it gives a little bit more power as well. That's what the satellite is going to look like. I'll show a more detailed picture of the mechanical arrangements in a second, but it's a 3 UKube sat, and it's got, apart from this deployable panel, it's got 2 other deployable panels here, which are increasing our power, so we should have quite a lot of power available for running the various payloads. There are a few other things which you can't easily see. There's a sort of like a window thing there, where one of the payloads will have a pop-out unit which will take pictures, and it'll have its own antennas. Underneath there's an S-band patch antenna, and it's got 4 whip antennas, 2 for 2 meters, 2 for 70 centimeters. Mass 4 kilograms, power greater than 5 watts on average, hopefully quite a bit more than that. Active magnetic control, 2-axis, about 5 degrees or so of positioning uncertainty. There's an experimental 3-axis reaction wheel package, so if that works it'll be 3-axis stabilized, which will help a lot in targeting the camera. The mission interface computer is somewhat novel because it's based on an FPGA. Maybe. Hopefully that'll work fine, but if not, there's a secondary processor which is able to do most of the commands and reboot the FPGA in the event of a single event upset. There's a lot of mass storage memory for storing files and images, gigabytes worth of that. The comms are monopole whip antennas. It's a 70 centimeters up, 2 meters down satellite, about 300 milliwatts on 144.820. The STX, the S-band transmitter, 7 dBi patch antenna, and about 1 watt of RF. Because that's using rather a lot of the power, that will only be on when it's over a suitable ground station. And the data rate, I guess you'll find interesting in a second. It's the standard format of boards on the stack with the 104 connectors, similar to FUNcube and all the others. That's a slightly more detailed mechanical drawing showing the various bits and pieces. There's quite a few of these as it's going through its development phase. One of the issues that is quite important is what happens if something goes wrong. As far as possible, there are multi-thread ways of getting through the system. There are a few things that are single thread, which is unavoidable in a CubeSat, but there is some redundancy. All the microcontrollers have watchdogs, for example, and we can set hard resets, not just via the uplink, the UHF uplink from the ground stations, but also the FUNcube will be able to send a reset to the main system as well. Okay, in orbit we would be able to reflash the FPGA if we upload a new file. Obviously that's something you don't really want to do unless you're absolutely sure that the file you're flashing it with is okay. But it has that capability should there be some problem, some failure which requires us to change the operation of the mission. FUNcube operates independently of the control and data handling system. The EPS is, well, this is Clyde space, they're saying it's analog in design and radiation tolerant. The secondary processor, which I mentioned earlier on, can take over the core functionality. There's a dual I2C bus, so most systems have 2 methods of getting information back to the main computer. And there are various things to do with health monitoring. And of course we've got dual links. With the FUNcube and the UV transceivers, we have the option to have 2 different downlinks. So if one of those downlinks fails, we should be able to download a lot of the telemetry, one or the other. So major new stuff is the S-band transmitter, which is 1 megabit per second, QPSK, half rate coded though, so only actually 500 kilobits per second, but that's quite a lot for a CubeSat. The active magnetic control, the 3-axis control and stabilization, the reconfigurable in-orbit FPGA, and the higher output through rather a large number of deployable solar arrays. This is just showing the overall structure. I guess it's not all that easy to read that, and in view of the fact that we started late, I won't go into any great detail on this because I guess you'll be able to look this up on the web. But that shows you how everything combines with everything else in the inside the satellite and how the interfaces are made. Let's move on to the payloads. There was a competition for the payloads which came up with the final down selection back in about March. And the first one is the CMOS imager demonstrator from the Open University. It's a new sensor which will take pictures of the Earth and a new type of CMOS sensor. And the other thing that this will do is see what happens with radiation and what the radiation effects are on this new sensor. So this is space qualifying type application, but should also give us some nice images. Hence, we need the high capacity downlink because these images will be pretty large. There's Janus, which is an Astrium payload. It's a true random number generator. It's I guess most people know you can't generate random numbers using computers because of their algorithmic nature. This is hoping to use cosmic radiation acting on an FPGA to develop, to generate random numbers. Now that allows secure communications, and that's not just military type communications, but things like your banking details and anything else. A lot of these things go via satellite, and secure communications is something you want. Again, this is in orbit reprogrammable as well. Then there's TopCat. This is a topside ionosphere plasmasphere computer-assisted tomography. Complicated name. I guess everyone's familiar with GPS these days, and the fact that the ionosphere causes errors in GPS positioning due to electron density. So you get a delay. There's an onboard receiver which allows you to measure that unexpected delay or excess delay, and that's used to map the ionosphere as the satellite travels through it. So this will allow us to look at solar storms, space weather, the effects of the sun, and we're coming up to the solar maximum, so there might be some quite interesting stuff going on during the orbit, during the mission phase. So that's being run by the University of Bath. And then there's my Pocket Cube. This is a rather interesting payload. It's being produced by the UK Students for Exploration and Development of Space, UKSEDS. It's a pocket satellite, as in it's effectively a CubeSat based on a smaller cube format, about a quarter of the size. And that satellite itself has several payloads in it, and I've listed some of the major ones here. There's OpenSpace 365, Orbit, which is an outreach experiment, Orbit View, which is a pop-out camera, Superlab, which is looking at superconducting materials and the effects of radiation on those, and Super Sprite, which is a nano or pico or whatever this next one down is, satellite on a chip. So that's a satellite inside a CubeSat with another satellite inside that. It's like Russian dolls. My Pocket Cube payloads in more detail. OpenSpace 365, now you need to think about this if you're interested in it. It's an Arduino processor. And effectively you're able to submit a software program up to 32 kilobytes in size, which can return up to 1 megabyte of data. There'll be 365 of these programs, up to, and that's for school pupils or university students or hobbyists like radio amateurs. Develop software, fly it on the satellite, and get your results back from a system in space. So that's an exciting outreach thing for UKSEDS. The sensor itself has got quite a few capabilities. It's got abilities to measure voltages and currents and temperatures, and it also has an imager on it. So that's probably going to be sometime around September. I think they might actually have opened up the competition now for people to submit what their ideas are to this. Hopefully quite a lot of these things will be done in advance, so we don't have to upload them before the flight mission. So it will go up with several preloaded, and then as the mission progresses we'll be able to upload a few more of these programs to the I think it's got 2 gigabytes of flash memory on this payload, so there's quite a lot of space for programs and things. Then there's Orbit View. This is a rather interesting thing. It's I guess you can see that there's a spring there, and there's a camera here, and there's a mirror here, and what isn't shown here are some antennas which pop out as well. This thing will pop out of the side of the UKube after launch. Hopefully it will pop out after it's left the P-pod. That's something that I'm not worried about, but I'm assured that it's okay. And this mirror and this imager here gives us a view back of the satellite, so we can look at the satellite whilst it's in orbit. Now, it might not be very exciting, it might not change very much, but we can see if the antennas have deployed, and we can take nice pictures of backgrounds and things. And there's another camera which will be looking out, so it'll allow you to look out of the window, Google Street View style. I guess there's not likely to be, or hopefully there isn't likely to be anything very, very close that you can see with that camera. And then the Super Lab. This is a material science experiment. This is an example of a thin film superconductor. They'll be measuring the resistivity of that, so it's not clearly a perfect superconductor, but the effects of temperature and radiation on the resistivity of these new superconducting thin film materials. And then we have the Super Sprite, which is a satellite on a chip. So that's pretty much what it looks like. It has solar cells, it's got energy storage, it's got a microcontroller, and it's got a transceiver, which is a spread spectrum at 70 centimeters downlink. All that's inside the pocket satellite. Now, I have one or two concerns over this because 70 cents happens to be an uplink, and it's downlink, but it's only got about 10 milliwatts of power, and we can command it to be off during the command phase. But it's a very interesting concept to have such a tiny little satellite inside a satellite inside a satellite. The other payload, of course, which we all spoke about in great detail yesterday, is FUNcube-2 on UKube. I think we ought to come up with a better acronym for that. The first one I came up with was FU, and I don't think that's a particularly good one. So I think we should come up with a different acronym so that we don't have to keep saying FUNcube-2 on UKube 1. Anyway, it's pretty much FUNcube, but it's minus the platform and the power supplies and everything else, but it'll have the same capabilities. The FUNcube team are building it, so they'll be able to tell you in detail exactly what it's going to be able to do. But it's got the transponder, it's got the beacons, it's got the telemetry downloads and everything else. And all of this was presented yesterday, so I'm not going to dwell on that at all. These are the antenna configurations. We've done a bit of modelling of these, and we've done a little bit of chamber testing to work out the radiation pattern. One thing we're a little bit worried about is if there are any nulls with the satellite being free axis stabilised. You don't want a null pointing straight down towards the ground, or a null on the horizon if you're trying to command it. So we're looking at that at the moment. The S-band patch here is on the bottom on the facing face. That's not ideal because of the radiation pattern of that. It means it's not radiating a lot towards the edges, so you need a fairly high elevation angle to receive it. If you want to receive it for the whole pass, you need something around 2.4 metre dish. When it's overhead, a 60 centimetre dish will be fine. But as I said, this will only be generally on unless there's a lot more power available than we hoped, which is possible, I guess. This will only be on when it's in view of a command station. All the command stations are in the UK at the moment, i.e. it'll be on over the UK. Right, now the bit I'm working on is the ground segment. So I guess this is a rather busy diagram, but it's trying to show what all of the communications links are throughout the satellite and how all the data gets back up and down to the ground. The UHF VHF is the primary link for all data. The S-band is secondary link for data only. There's no S-band uplink. If the S-band doesn't work at all, the mission is still 100% successful. But we want it to work. We have a primary ground station, which will be the RAL STFC one at Chilbolton or at Rutherford Appleton Laboratories. We've got two for redundancy. There's two stations up in Edinburgh, one at the University of Strathclyde and one at the University of Dundee. We're also looking at possible work with GENSO and other radio emitters. And everything will come via the internet, via web interfaces. The requirements. Minimal, as in without the S-band, about 2 megabytes per day, exclamation mark. That's quite a lot, so we need to worry about that. There's about 300 kilobits per orbit for each of the payloads, 150 kilobits per orbit from the platform. There are 16 orbits per day. Add 100% to that and you end up with 2 megabytes per day. Total pass time is 30 minutes on a good day if you're lucky. So to achieve that, you need a minimum of about 1200 bits per second continuous downlink. We will be using 9K6 board GMSK with AO40 style FEC. That's about 40% efficient in terms of data per bit per second. That gives us a small margin. So we might well be looking for other ground stations who are not within the UK footprint if we find that we don't have enough ability to download everything. But we should be able to do the mission with that downlink. Uplink is a lot less critical because there's a lot less to send on the uplink. And that's also using 9K6 board, but we're not using any of the FEC on that because we don't need to, we just use more power. The other thing to say about the downlink, the AO40 style FEC, that is an option. It can also do G3RUH style, but GMSK, AX25 without any FEC, which will give us a much better data rate, but of course we'll lose a lot more bits through bit errors. So, right. In terms of the link concept, commands are going to be individually acknowledged, but downloading data files won't. We're going to go back to the old USAT trick of dumping data, working out which bits you haven't got, sending up a holes list, and getting the satellite to send the missing bits. This is just how everything's going to be arranged in terms of the ground segment. So there'll be ground stations, Dundee, Strathclyde, Rowell, Chilbolton, on some sort of network. They'll talk to a primary server, which will be controlled. External people will not have access to that, apart from Clyde Space, because they're the mission controllers. All user contact will be via a web server, and there'll also be an archive. In terms of the hardware, primary downlink is 145840, 300 milliwatts GMSK. If you do a link budget, which I'll show on the next slide, you discover you need a decent Yagi. To do that, you can't really receive that with a monopole at the edge of coverage. We're going to be using a 910H with an LNA and a filter, and a 10-element cross Yagi for the downlink. S-band, I already mentioned, 1 watt, 1 megabit, 2.4 meter dish required. On 70 SAMs, you need about 50 watts or so into a 90-element cross Yagi. I'm not sure quite how those numbers go with FUNcube. I think FUNcube will probably, the transponder will require a bit less than that. This is, again, this is really for reference. You'll have a look at it later and tell us where we've gone wrong if you notice any errors. This is a link budget, and the thing that you really have to take account of now on a 2-meter downlink is this particular line here, which is the atmospheric noise temperature, including the local level of RFI and pollution. If you look at two different sites, say a city centre site and a quiet site like Chilbolton Observatory or Rowell, the difference at VHF, we've got a positive margin here, about 12 dB. We've got a negative margin there. That's just because of the noise. Now that gets a lot better as soon as you start getting up above 0 degrees elevation, but it does mean that in a noisy site you don't have enough visibility of the satellite to download the data that you need to download if you want to download 2 megabits or so per day. And that's one of the reasons, or one of the primary reasons for using FEC, so we can get that margin up a bit. Typical hardware, it's pretty much, this is a picture of the Chilbolton, well, it's the 4.5 meter dish, and these are the VHF and UHF Yagis. It's the usual setup with an ICOM IC910H, stuff on the indoors and stuff in the mast, circular polarizers, filters, Aziel rotators, that sort of thing, fairly standard. This is a picture of the system that they've got up at University of Strathclyde in Glasgow. They have got VHF, UHF only. They've got a couple of crossed Yagis. There's one there and there's one there, one there and one there. So they've got left and right at the same time. The satellite is actually linearly polarized, so we need circular because we don't know its orientation, but we only need left or right. We don't need left and right, and to be able to switch between the two. Dundee don't have a VHF UHF system at the moment. They have several dishes like this one, which is on top of a building in Dundee. What they're going to do is they're going to put a Yagi, a VHF UHF crossed Yagi on a boom stuck to the back of the dish, so it'll stick out of the side of the dish and it will track along with the S-band ground station. That's a 4.5, or was it a 4? I think it's about a 4 meter dish that they're intending to use for this. and this is their rather nice computerised ground station control room, and a very nice picture of the local area up there. If anyone's ever been up there and stood on the roof of the buildings, it's the most wonderful view, but there's a heck of a lot of wind, so it needs to be pretty robust system up there. Now, software. This is where we're starting to get into areas where we're going to need some help, ideally from the community. It's still under development. It's likely to be Linux-based for reliability. We've got a central server, we've got a web server, we've got a data archive. I think we can do a data archive, but we need to talk to various people about how we're going to do that. The central server doing the scripting and commands, that's something that we're fairly sure about as well. Web server, again, the problem with all of these, we've got the hardware and we've got some software, but it could be a lot better if we got some assistance from people who really know what they're doing. My current worry is more to do with ground station control and demodulation and decoding and packetization. Because we're using FEC and because we're using 9K6 GMSK, we could use a standard KPC 9612 TNC in non-FEC mode, but there's a bit of a mismatch between GMSK and FSK, which gives a few dB of loss. So ideally, we would like to use a software modem and get those few dB back. So that requires some work at the moment, and that's something that I've been talking to Scott about and various other people to see if we can get some help to develop some software to do that now. So that pretty much covers it. There's another gratuitous image of UKube from the people who do the design. At this stage, are there any questions?
Gosh. Right, thanks, Mike.